Work energy theorem. Work was defined to be force into displacement. Still precisely in vector notation it is force dot displacement. If you consider displacement as dl, a tiny infinitesimal displacement, then f dot dl will give you a small infinitesimal work done by the force. And to get the total work done, you have to integrate f dot dl. And this integral is a line integral or a path integral carried over along the path of the particle from initial position of the particle to the final position of the particle. The work energy theorem states that the net work done on a particle equals the increase in its kinetic energy, which means if a particle is subjected to a force, then the particle starts moving and it speeds up. You will see that as the particle speeds up, its kinetic energy increases. And from where this kinetic energy comes? The claim is that that kinetic energy is nothing but the work done by the force. The work done by the force is going to express itself as kinetic energy in the particle. So now by using this theorem, we will try to deduce expressions for kinetic energy in relativity. And this theorem, this work energy theorem, also holds relativistically. So now with force defined to be rate of change of momentum, we will try to elaborate this integral. So work done is equals to the integral dp by dt dot dl. And we will divide dl by dt and multiply it by dt to compensate. And you can see that dl by dt is nothing but u, which was the velocity of the particle, and dp by dt is the force. And now the integrand dp by dt dot u can be expanded, and we know that the expression for p is the momentum, relativistic momentum p is mass into the ordinary velocity divided by square root of 1 minus u square by c square. We will use this expression and we expand the differentiation, and this is what you get. You have to differentiate it by the product rule by considering m divided by square root of 1 minus u square by c square as one function and u as another function. You can see here the thing which is inside the parenthesis has been differentiated by using product rule, and this is what you are going to get. And further, the expansion of this differentiation gives you this by making use of the chain differentiation, and this we have done before, and this leads to this expression. And now, and on the other side, this differentiation du by dt can be called as a, the ordinary acceleration. And there is a dot u outside this parenthesis, which when used with the expression, then it will yield you the u dot a, the expressions u dot a, and from and this simplifies into this expression. And from this expression you can take u dot a and 1 minus u square by c square to the power of 3 by 2 common. And this is what the expression reduces to. And now you can see that u square by c square can be cancelled from here and here, and this will just become 1. And the expression is just mass into the ordinary velocity divided by 1 minus u square by c square to the power of 3 by 2 dot du by dt. And by observation, this expression, this term can be seen to be d by dt of mc square by square root of 1 minus u square by c square. By observation means you can start from here, expand this differentiation by chain rule, and you will end up here. So hence we are going backwards, and we claim that this expression is equal to this expression. And now substituting this expression back into the expression for work done, you will get this, and removing dt, and this is just integral of differential of mc square by square root of 1 minus u square by c square. And the differentiation is carried from an initial position to final position, and the differentiation is very simple, and this is just nothing but mc square by square root of 1 minus u square by c square. And as far as the integral limits are concerned, the integral limits are taken from an initial velocity to a final velocity. Let us consider that the particle is at rest initially, that is u equals to 0, and it accelerates to a final velocity u, and then the integral limits will be u equals to 0 to u equals to u. And then after substitution of the limits, you will get mc square by square root of 1 minus u square by c square minus mc square as the expansion, because you can see when you apply the lower limit, when you are taking u equals to 0, the denominator will become 1, and hence the whole expression is just mc square. And by the work energy theorem, this final result is claimed to be kinetic energy. So, and now we got the expression for kinetic energy, so which will be nothing but mc square by square root of 1 minus u square by c square minus mc square. And we will identify mc square by square root of 1 minus u square by c square as total relativistic energy E, and the mc square as E naught, which is nothing but the rest mass energy. Rest mass energy is nothing but the relativistic energy when the particle is at rest. If you substitute in the relativistic energy u equals to 0, then this expression will end up into mc square. That we call it as E naught. And now plugging back, then Ek, the kinetic energy, is the difference between the total relativistic energy with the rest mass energy. That is, Ek equals to the total relativistic energy E minus the rest mass energy E naught. And also we can show that by taking the expression for kinetic energy, take mc square common out, this will come into 1 by square root of 1 minus u square by c square minus 1. And we will expand in the non-relativistic regime, means when the velocity of the particle is very smaller than that of the velocity of light, then the square root can be expanded in powers of u square by c square by using the binomial theorem. And this gives this expression. So Ek, we will consider this as 1 minus u square by c square to the power of minus 1 by 2. And when you are applying binomial theorem, you can see that 1 plus, let this expression be x to the power of n. And the binomial expansion of this expression is 1 plus n into x plus n into n minus 1 into 1 by 2 factorial into x square. So likewise the expansion goes. And whilst after simplification of this expression, you will get this one. And this minus 1 which was here will get cancelled with the first term of the expansion, and you are left over with only the powers of u. And therefore this will be the expression for kinetic energy when you expand it with the binomial theorem. And the leading term reproduces the classical formula for when u is very less than c. That means when u is very less than c, these expansions which are having the c square in the denominator will become approximately equals to 0, because it is division by a bigger number comparatively when u is small. When u is small, dividing by c square will make these terms very small, which is approximately 0, and then all the higher order terms of u square will vanish and you are left over with only the first term. And this first term, Ek equals to half mu square, is nothing but our kinetic energy formula in classical mechanics. So it shows that the relativistic kinetic energy formula will also reduce into the classical mechanics non-relativistic kinetic energy formula, which is nothing but half mu square. Thank you.